top, and there's actually like an algebraic test that we run to check for symmetry. If you are checking for symmetry over the x-axis, remember symmetry just means if you fold it on that line, everything would match up, right? So if you're checking to see if you are symmetric over the x-axis, so could I fold my graph in half on the x-axis and everything match up? All you do in the equation is substitute negative y for any positive y's, or vice versa. Basically change the sign of y, okay? So if I were to do that in the first equation that was given here, right, I would have then negative y is equal to x squared plus 2, okay? Whenever you plug it in, you simplify if you can, right? In this particular case, there's not really anything to simplify. And it should look like the original. Well, there's nothing I can do to simplify what's written here. And it does not look like the original. So I would say that no, this one is not symmetric on the x-axis, okay? Let's try it in this second equation here. So this second equation was y squared. So I'm going to plug in a negative y in place of y. So I'll have negative y squared times x equals 1. Now I could do a little simplifying here, right? Because I do have a negative y being squared. And remember, squaring something means to multiply it by itself, right? So negative y times negative y would actually become positive y squared. And now this one looks exactly like what we started with now that we've simplified, right? So this answer would be yes, this one is symmetric across the x-axis. Okay? And then we got one more equation we can try it out in. So this one is the absolute value of x plus the absolute value of, again, remember we're going to replace y with negative y equals 1. And like we discussed yesterday, absolute values are distance from 0, right? So it's not ever going to be negative. So the absolute value of negative y is just y, right? It doesn't matter if I plug in a negative or a positive y, I'm still going to get out a positive y from there. And this one looks like what we started with, so it is also symmetric about the x-axis. Okay? So if you can make it look like the original, then the answer is yes. If you can't, then the answer is no. Okay? Okay, if you want to check for symmetry on the y-axis, we are going to sub out any x's for a negative x. Okay? So same process, just switching out the x's. So for that first equation, I would now have y is equal to, instead of x squared, it'll be negative x squared, because we're going to replace the x, plus 2. Well, kind of like we said earlier, negative x times a negative x is going to become a positive x squared, right? So this becomes y equals x squared plus 2, which is just like the original. And as long as we can make it look like the original, our answer is yes, it is symmetric. Okay? All right, and then we would have the same thing, but for that second equation. So I'm going to have y squared times negative x equals 1, right? I can multiply those two together. Really, all that's going to happen is that the negative is going to come to the front, right? So it looks like this, which is not what the original looked like. So this one is not symmetric on the y-axis. And then finally, in that absolute value one, kind of like last time, it doesn't matter what I put into the absolute value, it always comes out positive. So this one will go back to looking like the original. Therefore, we would say yes, this one is symmetric on the y-axis. All right. We also can check for symmetry on the line y equals x. And just like whenever we were reflecting it, what we're going to do here is switch the places of x and y. Okay? So to run this test, we will switch the places of x and y. So instead of y equals x squared plus 2, it's now going to be x equals y squared plus 2. Now, if possible, we would try and solve for y, right, so that it would potentially look like that first equation. I can subtract 2 from both sides, right? So now I'd have x minus 2 equals y squared. And the original equation just had y, not y squared. So to get rid of that square, I'd have to take the square root, and I'd have to do that on both sides. So I've got y equals the square root of x minus 2, which is definitely not what we started with, right? So this one would be no. Okay. Same idea for the next one. We're just going to switch where the x and the y are in the equation. So instead of y squared, it'll now be x squared times y equals 1. Well, there's no way, right, that we're going to be able to make that look like the original. So again, this one is not symmetric about the line y equals x. Okay? And then for the last one, we'd have now the absolute value of y plus the absolute value of x equals 1. Well, addition doesn't matter the order, right? So I could very well switch them back, and this would still be equivalent to what I started with. So this one is symmetric on the line y equals x. Okay? And then the last thing we can check for symmetry on would be that origin. And just like when we reflected, we do the same thing. We change the signs of both the x and the y. So for that first one, I'd have negative y is equal to negative x squared plus 2. Now that y is going to stay negative, but when I square the negative x, it will become a positive x squared again. Right, so part of my equation went back, but not the whole thing, right? It still doesn't match that original. We don't typically like to leave the lead negative, so you might have divided all of this by -1 so that you have a positive y in front, but then that messes up the signs on the other side, right? So now you'd have negative x squared minus 2, which still doesn't match. So we'd say no. All right, for that second equation, we'd have negative y squared times negative x equals 1. Well, again, I can square the negative y, and it'll become positive y squared. But when I multiply it by a negative x, it's still not going to look like the original, right? So this is what we got. Does not look like the original, so we'd have to say no there. Okay? And then finally, in that last one, we're taking the absolute value of x, adding it to the absolute value of y, but now they're both negatives. But with an absolute value, as we know, it'll become positive. So this one would revert back to how it originally looked. So this would be the only one that we can say, yes, it is symmetric about the origin. Okay? So the tests for symmetry actually are a lot like the same rules for reflecting the points, right? Whenever we reflected across the x-axis, we said we'd change the sign of y. When we were reflecting over the y, we said we'd change the sign of x. When we were reflecting over the line y equals x, we said we'd switch x and y. When we did the origin, we said we'd change the signs of both, right? So pretty much the same, but in an equation instead of on coordinate points. And again, it has to look like the original in order for you to say that, yes, it's symmetric. All right, and then if you'll flip it over onto the back, there are two other things that we can test for. Besides symmetry, we can test to see if the function is even or odd, or potentially neither, right? We're not talking about the degree of the function necessarily here, so it could be neither. So it says you have an even function if f of x is equal to f of negative x, okay? basically kind of like what they were saying on the front, like take the x, replace it with a negative x. And if they're equal, then you automatically know, yes, it's even. So they're saying if you were to do that right here, if you were to go plug in a negative x, right? Sure enough, when I square the negative x squared, it's going to go back to looking exactly like the original, right? So, because when you plug that in, it's the same as the original, we can say that it is even. So, same as the original. So, this is an even function. But if you were to go plug in a negative x and it didn't go back to how it looked, then we could not say it's even. Okay. All right, to test for odd, you do the same thing but with your y's. Remember, f of x is the y value, right? So what they're saying here is that if you plug in a negative x, it should change the sign of your y, okay? Or basically, in other words, all the signs should become opposite, okay? So what this part means, you might even put this in parentheses, is opposite signs of the original is what we're testing for here. So for the even, we wanted it to look exactly the same, right? Here, when I plug in a negative x, I want it to be the same, just opposite signs. So again, I'm going to plug in a negative x. So I'd have f of negative x would be equal to negative x cubed plus 2 times negative x. Okay, well, raising something to the third power isn't going to make it positive, right? So this would be negative x cubed, and 2 times a negative x would be negative 2x, right? So it does not look identical to the original, so not even, right? But if I compare this to the original, it's the same, just opposite signs. So this one would be odd because the signs are opposite. So these two signs are now opposite, so this is odd. So this is the opposite signs from the original. So it is odd. Okay. It goes on to say here, substitute in negative x for x into that function x cubed plus 2. And they asked, does this function satisfy the definition of an even function? Does it satisfy the definition of an odd function? So let's give it a try. So now I'm going to sub in negative x into this function. So it's similar to that second one, but not quite the same. So I'll just have negative x cubed plus 2, right? Okay, well, like we said, when you cube a negative, it stays negative, right? So this would be negative x cubed plus 2, right? Okay, does it look identical to its original form? So is it even then? No, because for it to be even, remember we said it has to look identical to the original. But it also is not the exact opposite of it either, right? This part is, but this part is not. So it also does not meet the definition of being odd either. So this one would be considered neither even nor odd, okay? So therefore, this function is neither even or odd. So basically, you're running the same test to determine even or odd. It's how the final one looks that will let you determine whether it's even or odd. So just replace all the x's with a negative x. If it looks the same as the original, even. Opposite of the original, odd. But if you've got some mix in there, then it's neither even or odd. Okay? All right.